This video goes over the example where I want to prove that the limit as x goes to a half of 1 over x is equal to 2. And as usual, we're starting by understanding what is f of x minus L. So in our case, f of x minus L, our function is 1 over x. So we get 1 over x minus 2. And if we think about our x minus c term, since the limit is approaching 1/2, this should be x minus 1/2. And as usual, I want to know, how does 1 over x minus 2 depend on the expression x minus 1/2 in absolute value? Now, looking at my expression 1 over x minus 2, it may not be immediately obvious how I'm supposed to manipulate that algebraically to see x minus 1/2. But notice in my x minus c expression, x needs to be in the top, whereas in f of x minus L, x is currently in the bottom. So the first step is to try to change the way this looks so that I have x sitting up top. So I'm going to take my expression and I'm going to get a common denominator. So I'm going to have 1 minus 2x over x. And then I can split this apart across the division. And I don't quite have what I want yet. Notice that in my term, my x minus c term, I've got x and I've got a half, but notice that there's no coefficient in front of the x. So a first step I can do is to sort of just factor out this -2. So I get -2, what remains inside is minus 1/2 plus x over the absolute value of x. Now I can distribute the absolute values across and rearrange, and what I'll end up having is 2 times absolute value x minus 1/2, because the order of subtraction doesn't matter inside absolute values, over the absolute value of x. And in particular, I now have x minus 1/2 sitting by itself, left with 2 over absolute value x. And my goal, remember we said, is when you have extra stuff besides just your x minus c term, you want to try to bound it to make it go away before you choose your delta value. Now, 2 over absolute value x is not a globally bounded function. When x is near 0, that is going to become unboundedly large. So 2 over absolute value of x is going to go to infinity as x approaches 0. So therefore, there is no global bound. When there's no global bound, remember we said we want to look for a local bound instead. And notice that as long as we stay away from 0, our function 2 over absolute value x will be bounded locally. So we can bound 2 over absolute value x locally as long as we don't allow our x values to approach 0, the place where it's unbounded. Now for us, in our problem, remember what we're doing. We are trying to find the limit as x goes to 1/2. And so as long as I'm going to choose a restriction on my x values that doesn't allow x to go near 0, ultimately x is going to be near 1/2. So for us, x is approaching 1/2. So we know we're going to be working in delta neighborhoods that are centered at 1/2, and then it's going to go up to 1/2 plus delta, 1/2 minus delta. And we're saying we do not want to allow x to approach 0. So we need to make sure our restriction creates some positive distance between the x values that are in my neighborhood and the number 0. I don't want to be able to find a sequence of x values from my sequence that could somehow converge to 0, because then I would be unbounded. So what we're going to do is we realize we need to keep x away from 0. So we can use any delta strictly less than 1/2, since that is the distance between c and 0. So 1/2 is the distance between our c value and 0. And we need it to be strictly less than 1/2 because we don't want to allow our values to roll straight up to 0. So if I'm picking a number that's less than 1/2, maybe I want to use delta equal to 1/4 because that works out nicely. So we're going to require delta to be less than or equal to 1/4. Now, if I require delta to be less than or equal to 1/4, then notice that when x is in my delta neighborhood of 1/2, that says that x has to be in the interval. We're going to be going left 1/4 and right 1/4. So that's going to give me 1/4 to 3/4 as my location of x, just being in a delta neighborhood of radius radius less than or equal to 1/4. Okay. When that's true, I need to figure out what I can say about 2 over the absolute value of x, because that is the expression I'm looking to locally bound. So when I look at 2 over the absolute value of x, which in our case, since x is in 1/4 to 3/4, this is a positive value, so I can just drop my absolute values. That means that I'm going to be restricted between 2 over 1/4 and 2 over 3/4. So that's 8 and 8/3. So what I get is that 2 over x on this interval is going to be strictly larger than 8/3 and less than or strictly less than 8. So I can use this bound 2 over absolute value, 2 over x is less than 8 when delta is less than or equal to 1/4. So when I go and I look at my expression I was computing before, remember we were focused on replacing 2 over absolute value x. So we had x minus 1/2 times 2 over absolute value x. And now we're able to say that this is strictly less than x minus 1/2 times 8. And ultimately, I want this to be less than epsilon. I know I can make my x minus 1/2 term less than whatever delta choice I want. This tells me that I want my delta value right here to be epsilon over 8, so that when I'm done computing, I ultimately arrive at epsilon. Okay. So going back, we need to make sure we understand what restrictions we've used. So in order to be able to use our local bound, we needed to know that delta was less than or equal to 1/4. And then ultimately we need to know that delta is less than or equal to epsilon over 8 in order to make the rest of our argument work once we substitute our bound on 2 over x. So it looks like overall the delta that I want to use is going to have to be a minimum of 1/4 or epsilon over 8, whichever one is smaller. Now I can write my proof for my formal argument. So again, I'm using the epsilon delta definition here, so that means first thing I should do is introduce epsilon, so let epsilon greater than 0 be arbitrary. Then we introduce our delta value, so delta is the minimum of 1/4 and epsilon over 8. Note that in either case, whether or not it ends up being 1/4 or it ends up being epsilon over 8, we still have a positive real number. Then we let x be in the domain of our function. Now remember what we're proving. We're proving that limit as x goes to 1/2 of 1 over x is 2. So our function is 1 over x. So we're going to be working in the domain of r minus 0. So x can't be 0. And then we're going to assume that 0 is less than the absolute value of x minus our c value, which in this case is 1/2, which is less than delta. From here, before we get started with the rest of our argument, we should probably point out that we now have a local bound on that expression that we need to get rid of. In particular, that's 2 over x. So we want to say, since delta has to be less than or equal to 1/4, x being in the delta neighborhood of 1/2 implies that, remember we said that meant that 1/4 was less than x, which is less than 3/4, because we had an interval that was centered on a half, and we said it only work with a radius of 1/4. And so in particular, we're able to say in this case that when I look at 2 over x, we said that was between 8/3 and 8. So we're going to be able to make a replacement. 2 over absolute value of x, we're going to be able to say is less than 8. That's our local bound. Now we're ready to introduce our f of x minus L expression and show it works. So that's 1 over x minus 2. Remember, our first step was to get a common denominator. Then we split it apart. Then we factored out this -2. And we rearranged. And we said, oh, now I can replace that 2 over absolute value x part with being less than 8. So this is less than 8 times x minus 2. I'm just substituting my bound here. Then I know that's less than 8 times delta. Delta is a minimum, so it has to be less than or equal to both of the things that that are in the list that you're computing the minimum of, in particular, epsilon over 8. And ultimately, epsilon pops out. So by definition, the limit as x goes to 1/2 of 1 over x is equal to 2. So this offers us another example of when you need to be able to try to create a local bound, which requires first restricting delta. In our example that we did in class of x squared, we needed to restrict our x values to stay away from infinity because that's where x plus 2, our extra expression, was unbounded. Here, our unboundedness happens at a finite location, in particular near 0. And so we needed to choose a value of delta that meant that being in the delta neighborhood didn't allow you to run right up next to 0 and become unbounded. That's why we chose a delta value less than or equal to something that would absolutely not include 0, would create a wall essentially between the left side of the neighborhood and where x equals 0 is.